Hey, pre-calc students, this is going to be a continuation of functions. Today we're talking about the concept of symmetry within different equations. So if you want to take out some paper, this is not included in your packet. You'll be taking some quick notes by hand. And there are three main types of symmetry that we'll explore as far as different relations and functions are concerned. And the main ones that we'll see are x-axis, y-axis, and origin symmetry. So here's kind of a quick graph to illustrate each of those three cases that I think would be nice for you to have in your notes as well. If you're looking at these three examples, x-axis, y-axis, and origin, I hope that you're making some conclusions about maybe some ways that we can test to see if something has and exhibits these types of symmetry. One quick note, though, is that if something does exhibit x-axis symmetry, it's not a function. Very clearly, x-axis symmetry is going to fail the vertical line test. So it would be considered a relation, but x-axis symmetry means it's not a function. Y-axis and origin, those can both very clearly be functions here. So what are we going to do as far as the test goes? Well, if we're testing for x-axis symmetry, it says if the equation remains the same when you replace, I'm going to say here, y with negative y. Okay, so if that's true, that I can take my equation and replace y with negative y, then that has x-axis symmetry. Notice how, for example, in this graph, a y value of 2 and a y value of negative 2 correspond with the same value of x. So if you can replace y with negative y and nothing changes, then it has x-axis symmetry. So it probably won't be a huge jump for us then to say that if I can replace x with negative x, then something would exhibit y-axis symmetry. And I hope that these tests sound familiar because you did do this in Algebra 2. So we've got x-axis symmetry, we've got y-axis symmetry. And then finally, the last case for origin, essentially you're doing both at the same time. So you're going to do x with negative x, and at the same time, y with negative y. And if the equation remains the same from making both of those replacements, then the conclusion is that we have origin symmetry. So if you look at some graphs that have origin symmetry, the point 1, 1 would correspond with the point negative 1 in this case. Okay, so we'll see that come up in other examples of graphs and functions that exhibit origin symmetry. So let's kind of jump right into this. There are three ways that we're going to sort of determine symmetry. We've got numerical ways, graphical ways, and then algebraic ways of doing this. So the numerical way that we're going to look at this is by using a table of values. So what we want to do in our table is we want to pick some positive values of x and maybe the corresponding negative values of x and see what those y values are. And although we can have a calculator do this for us, we can probably, for this example, at least just to get started, y equals x squared. We should be fairly familiar with what this looks like anyway. In fact, since we know what it looks like, I'm pretty sure we know what kind of symmetry it has. But just to show you what it's going to look like in a table versus the graph versus the algebra, we'll do this to get started. Okay, so like I said, let's pick like some negative values of x, like negative 2 and negative 1. Let's pick those same exact positive values of x and see what the outputs are. So negative 2, when I square it, it's going to be positive 4. Negative 1 squared is going to be positive 1. 1 squared is 1. 2 squared is 4. So what's going on here? Well, since x and negative x have the same y value, and the same thing applies in the middle here, right? If you can replace x with negative x and have the same y value, the conclusion is we know we have y-axis symmetry. Okay. So y-axis symmetry exists when you can replace x with negative x, and that's true in this case. Graphically, what's going on here, y equals x squared, this is something that it's a really good function for us to analyze to get started because it's something that we're really familiar with. Boy, if I knew what the graph looked like, or I can easily graph that on my calculator, yeah, I can analyze that that has y-axis symmetry. Perfect. Now, the algebraic way of doing this, I'll tell you, this is going to be our default eventually. You're always going to do this algebraically when we get to a certain point in the process. I'm going to cheat a little bit and show you that because we know it has y-axis symmetry, I'm going to replace x with negative x and show that the equation remains unchanged. So if I do y equals the quantity negative x squared, squaring a negative x makes it the same thing as positive x squared, right? Negative x times negative x is this. So because that's the same as the original equation all the way back over here, if those two things match, that's the algebraic confirmation that yes, this has y-axis symmetry. For ones that we're not as familiar with, I mean, we definitely, I think, knew what x squared looked like. But if we're not as familiar, this is the way we're going to go about it. We're going to start plugging in negative x's where we see x's, and hopefully that will help us determine the symmetry. All right, what about x equals y squared? What's this one going to do? All right, so let's talk about numerically first. For this one, I'm actually going to encourage us. This is going to be a little bit odd, but I'm going to have us pick some y values that when I square them will give me the x value. We're going to kind of work backwards in the table. We're not really used to that, but I think it will help us with our case. Let's do like -4, -3, and then +3 and +4. Again, the only reason why I want to work backwards here is it's easier for us to think about what's the x value that goes with squaring these y values. Well, -4 squared is 16, and this would be 9. And then you would get 9 and 16, okay? Notice how whether it's y or -y, that the outputs are the same, okay? So if I can replace y with -y and get the same output, then this has x-axis symmetry. And maybe we're not as comfortable as what this graph looks like. Sorry, lights just turned off on me. There we go. What you can do to figure out what the graph looks like is maybe you can think about taking the square root of both sides. But what a lot of students forget when they take the square root of both sides is that you need to consider it's plus or minus the square root of x. The positive square root of x would look like that, and that actually doesn't have any symmetry at all. But if I also graph the negative square root of x, I get this. And wow, yeah, that definitely has some x-axis symmetry. So this is actually representative of the inverse of y equals x squared, right? When you switch x and y, that relationship is the inverse. And we'll talk more about inverses later in our functions unit. What am I going to do for an algebraic test? For algebraically, if it has x-axis symmetry, we should get the same thing if we replace y with -y. So it's going to be a very similar example to what we just did. Plug in -y where we see y up here. Squaring -y is the same thing as just y squared. Since this matches the original, my conclusion is that we have x-axis symmetry. So just to kind of show you what the table might look like, certainly on a graph we should be able to tell easily, and then what the algebra looks like to determine some symmetry here. Okay. On the back we have the cube root of x. Cube root of x. It's actually one of my favorite functions. I love it. All right. If we're not sure what it looks like, I'm going to choose some values. Oops, that's meant to be a table over here. I'll fix it. There we go. We'll make it a big XY table. I'm going to pick some values that I hope will make sense to you in just a minute here. So I'm going to pick like -8 and -1, and then I'll do the same positive values for x. Okay. All right, so why am I picking -8, -1, and 1 and 8? Because these are all numbers that are perfect cubes, right? So that when I take the cube root of those, I can find for some pretty nice y values here. All right, -8 would correspond with a y value of -2. The cube root of -8 would be -2, because -2 times -2 times -2 is -8. All right, cube root of -1 is -1. The cube root of 1 is 1, and the cube root of 8 is 2. Remember, you can take cube roots of negatives, because a negative times itself an odd number of times is okay. All right, let's compare these pairs right here. How about -8, -2, and then +8, +2? When the value xy corresponds with the same negative x, negative y value on the graph. What kind of symmetry does this exhibit in a numerical table? When xy is the same thing as, and it also corresponds with negative x, negative y, that's our case for origin symmetry. Now, the reason why this is my favorite function is that if you were to graph and plot these 4 points, like -8, -2, -1, 1, you're going to see that the graph looks something like this. Kind of looks like the radical part, but we also get all these negative x and y values on this side. And it reminds me of a certain dance. It's kind of weird, guys, but next time we're in class, remind me to show you the dance for the cube root of x. It's one of my favorites. All right, so we've got a graphical representation. Hopefully you guys can see that we have this correspondence that if I reflect these points through the origin, we have that symmetry here. This is a good example of a graphical representation for origin symmetry. So remember, the algebraic test is you have to have x equals negative x and y equals negative y. Okay, you have to do those at the same time, this and that. So if I go back to the original, that would say negative y equals the cube root of negative x. Here's how I'm going to simplify this to show that this is the same as the original equation, because I know this should be true. We've already determined it has origin symmetry. So it's going to be negative y equals the cube root of negative x is the same thing as the negative cube root of x. Why is that the case? Think of this as like a -1. The cube root of -1 is -1. So you can kind of bring that -1 on the outside. I just write it as a negative. And then if you divide both sides by -1 to get y alone, now it becomes y equals the positive cube root of x. And we see that that matches the original. So therefore, the conclusion is we have origin symmetry. Origin symmetry sometimes is a little weird to test with because you have to know some good algebraic tricks to make this happen. And just make sure you get y alone before you make your conclusion. Okay, once y is by itself, if it matches the original, which it does, there's my confirmation for origin symmetry. Okay, let's take a look at x squared plus y squared equals 25. Here's the deal. I'm all about the algebraic from now on, okay? So I want to make sure we focus on this technique right here. And I'm going to show you the 3 tests that we can do to see if this has x-axis, y-axis, and then origin symmetry. Okay. This is how you're going to set up your homework, by the way. I'm going to expect you to do algebraic testing. And I almost want you to write exactly what I have here. Write down the 3 cases and then try them. How do we do x-axis symmetry? You're going to replace y with negative y and then see if the equation remains the same. So when I plug in a negative y here, we saw this earlier, that if you square a negative y, it's the same thing as positive y squared. Well, that's definitely the same as the original. Therefore, this does have x-axis symmetry. Let me show you what the y-axis test would look like. Similarly, instead of replacing y with negative y, you're going to replace x with negative x and see if the equation remains the same. So when you square negative x, that's the same thing as positive x squared, right? So you get x squared plus y squared equals 25, and whoa, good thing I didn't stop at x-axis. This one also has y-axis symmetry. So we can have equations that exhibit more than one type. Let's just keep the ball rolling and try origin, which is both at the same time. Okay, x gets replaced with negative x, y gets replaced with negative y. And lo and behold, yeah, squaring each of those gives you positive x squared plus y squared, and that equals 25. So this one has all 3 types of symmetry. It has x, y, and origin symmetry. Holy cow. What is this a graph of? Well, first of all, I know it's not a function if it has x-axis symmetry. But do you remember what x squared plus y squared equals 25 looks like? It's not easy to graph on the calculator. You know, getting y alone is going to be a little bit messy. But maybe you remember that it is a circle whose center is the origin and whose radius is 5. So if you go 5 in each direction from the origin, sorry, I don't know how this is going to turn out, just a rough sketch, it's not bad. Notice how it has x-axis symmetry, y-axis symmetry, and then you can reflect points through the origin. and have that kind of symmetry as well. So it's kind of good to have a general knowledge of what it looks like, because even if I make you do the algebraic tests, you should know in the end kind of what your result should be if you know what the graph looks like. All right, I think we have one more example to look at, y equals x to the fourth plus x squared. I'm going to encourage you at this point. So again, make sure you're just doing this algebraically. I want you to hit pause, try the x-axis, y-axis, and origin tests and see if any of them work. By the way, the conclusion might be that none of them work and it doesn't have any symmetry. So just like in the last case where all three worked, maybe you'll find that none of them work. All right. So hit pause, try this one. I'm going to start going through the solutions here. Does this have x-axis symmetry? Well, we have to replace y with negative y and see what happens. All right, when you do this x-axis test here, to get y alone, just divide both sides by -1. So that's going to become y equals negative x to the fourth minus x squared. Okay, so that clearly, in my opinion, does not match the original up at the top. So I'm going to draw a sad face here. This does not have x-axis symmetry. Okay, moving on to y-axis. We need to replace x with negative x and see what happens. So negative x to the fourth and then negative x squared. We've done this negative x squared business enough to know that this is just x squared, right? Now, if I raise negative to an even exponent, hopefully you're good to know that that's also positive x to the fourth. If you raise this to an odd exponent, then it becomes negated, right? So this is x to the fourth plus x squared. Look at that. Same as the original. So we've got some y-axis symmetry. All right, finally, the last test for origin. If I do negative y here and I put negative x in both locations on the other side, this becomes negative y equals, we just saw what happened here, x to the fourth plus x squared. But remember, to get y alone, just divide that -1 from both sides to get this. Oops, this does not match the original. So we don't have x-axis. We don't have origin symmetry. This one only has y-axis symmetry. Okay, so next time I see you in class, we'll do a little bit more practice with symmetry, and then we'll go ahead and let you guys work on some homework. Have a great day.